My name is Luis, and I'm also at Penn. And this work that I'm going to talk about was also done with help of Debbie Fields and Yasmin Cafei. Thank you, Gaithri, and thank you, Jimmy, for introducing e-textiles to all of us. As we have discussed today, debugging is an inevitable and intrinsic part of learning to code. However, for some students, encountering bugs can generate a fixed mindset and emotional responses such as fear and anxiety that lead to disengagement and the avoidance of CS. Prior studies provide evidence of how mindsets play an important role within CS, as students with growth mindsets perceive bugs as opportunities for learning, and those with fixed mindsets become frustrated with failure and see it as a challenge to their intelligence. Thus, promoting a growth mindset in the classroom is important since debugging is such an essential practice, and persevering through debugging is critical for students' learning. Few studies provide a holistic approach to debugging that takes into account the relationship between thinking and emotion in learning how to overcome failure. Traditional approaches usually include teaching debugging strategies using checklists or solving problem sets or solving bugs designed by instructors. In contrast, we try to position learners as designers of bugs. And we think that by having learners design bugs, um, they we might be able to promote their growth mindsets in practice. So what we do in debugging by design is that we have kids create buggy projects rather than functional projects for their peers. Building on previous research on growth mindset, we investigate growth mindset in action, analyzing how students practice it while they are creating buggy projects. For this study, we situated ourselves in a diverse high school classroom that was implementing the e-textiles unit of exploring computer science. And we situated this intervention debugging by design right 3 quarters into the unit. So students already had some experience with electronic textiles, and they were able also to use what they learned in this experience in their final project. We analyzed 4 groups of students. In debugging by design, at the beginning of the activity, students discuss with their partners and the whole class different errors and problems they had encountered when working on their e-textiles projects. Then students planned their project and came up with a list of bugs, of intentional bugs they wanted to include in their designs. After receiving approval from their teachers, they made their buggy projects. Once they finished, they exchanged their projects with peers and spent one class period debugging. Early evidence suggested that when students consciously created bugs, they improved their abilities to detect and fix bugs, they collaboratively solved problems, and increased their confidence in debugging. In our analysis, we were able to see intersections between the cognitive challenges in designing code, circuit, and crafting bugs, and the motivational and emotional challenges often associated with mindset. We identified 5 emergent growth mindset practices or behaviors. Throughout DBDs, students purposefully chose challenges that led them to learn new things, throwing themselves into difficult tasks and sticking with them. Students persisted after setbacks. Setbacks can cause frustration, but at the same time can be great opportunities for learning. While working on their debuggings, the students praised each other's efforts, strategies, and processes. Student teams also embraced learning as constant improvement and looked for ways to improve their projects and their competence. This reflects a desire to learn, to get smarter, and acquire new skills. And the last practice we identified is developing comfort with failure, particularly by not being afraid of being wrong when asking questions, sharing failure with their peers, and embracing failure and imperfection as part of the process. We found 230 instances across 4 groups of students. In the figure, we can see the frequency of instances of each practice by the group of interest, as well as information about the context of each instance when they occurred and who was involved. It is worth noting that 56% of the instances occurred when learners made buggy projects for their peers to solve, and 78% occurred when peers interacted with each other. Although we also identified growth mindset practices when students worked alone or in learner teacher interactions. In designing debugging by design, we build on a tradition of constructionist activities that put learners in control of their own learning by designing applications for others and extended this concept by having students make buggy projects. By making learners designers rather than finders of bugs, we created an environment in which students were in control of creating mistakes. We suggest that our design focused, practice first approach may be particularly well suited for promoting growth mindset in domains like computer science that involve iterating, testing, and debugging. Our analysis of 4 groups of students provided insights into learners and how they develop their growth mindset practices and become more comfortable with debugging. Particularly, developing comfort with failure complements the practices mentioned in previous research, acknowledging mistakes and failure as an intrinsic part of the learning process. Combined, these practices promote debugging as a holistic process that involves thinking, motivation, and emotion. And that's it. Thank you.
Wonderful. Thank you. So I'm going to ask a question that we just saw in the chat. All right. So David asked, did you encounter bugs in the intentionally buggy projects? It seems like it might be a tricky thing to debug a bug.
Yes, and actually that was one of the fun parts of this. Students made bugs when creating buggy projects, and they made bugs in areas that they didn't even explore in the classroom. So in the classroom, we never talked about music and coding music on the Arduino, and students decided to code a song for one of their projects. So they were always looking for like more challenges, and those situations really happened when they were unintentionally creating bugs while intentionally trying to create bugs.
Great, thank you. Faye, I don't know if you wanted to ask your question. I'm happy to keep answering or asking questions in the chat, but.
Yeah, sure, I can ask my question. So I was wondering what were some characteristics of the bugs that the students created, like in terms of difficulty levels, etc.
Yeah, so the bugs varied across syntax, and they also varied across code and actual construction of the circuit and crafting. And we are working on another paper that kind of classifies all the different bugs that students made. I think one of the most interesting bugs that we found are intentional bugs. So bugs that don't have to do with the project not working, but have to do with the project not working as expected by the designers. So maybe they wanted the lights to flash, and then the project works, but the lights don't flash. And that is a very tricky bug where students have to think not only about, does this project work? Am I getting an error on the console? But is this project working as expected? Is this project doing what my peers told me it should be doing?
Great, thank you. So there's a lot of conversation in the chat. Let's see here. Any overlaps with known misconceptions? And I think this will be the last one for this so that we can go forward. That way we can have a larger conversation at the end too. So Luis, did you notice any misconceptions? Like known misconceptions?
Did they target misconceptions when they created those bugs? It's like, you know, things that people usually get wrong and are known to get wrong. And that may have happened unintentionally, not that they were taught that those are known misconceptions or something like that.
Well, I think that they did enter kind of like the first thing that we did in the activity was to have them reflect about bugs they had encountered before. So by creating a list and naming the bugs that they had encountered, they were already kind of thinking about what bugs could occur. And then in the process of designing bugs, they had to think not only of how to make a buggy thing, but actually how will my peers solve it? So a part of that, I guess, like addressing misconceptions was considering audience and thinking, if I put in this bug that might be a very mischievous bug, are my peers going to be able to solve it within the time that they're going to be given? Or am I making something that is just impossible for anyone to solve? So they were considering constraints in terms of creating bugs and considering what their peers would do when they encounter those bugs.
Maybe just to add there, like there were definitely, like, because I remember the list that we generated, there were definitely a lot of overlaps. Suchi, just to give a quick answer, like variables, like conditionals, those were still the same things that kids were grappling with. But it was within this context that now it became about what can I mess here so that my friends get really confused about debugging this buggy project. So.